Today we're looking at a very similar idea to what we talked about yesterday with the rules for sample proportions, and today we're looking at the rules for sample means. So if we're to take a bunch of samples from a population and they have an average value, so this is usually quantitative variables that we're talking about here, looking at the mean of all of those means. So a quick warm-up question here. Let's say that the average weight of all women at a large university is 135 pounds and a standard deviation of 10 pounds. So remember that empirical rule, 68, 95, 99.7 for the bell-shaped curves. In what range would you expect 95% of the women's weights to fall? Well, you could draw out a little bell curve here. Let's see. We know that the average, the mean, right there at the center of the curve, 135, and then the standard deviation is 10 pounds. So 145, 155, 165 out there. I'm not going to label each one of these. And then go down by increments of 10 to the left. So this would be 125, 115, 105, way down there. So we are interested in 95%, which would be, from our empirical rule, within 2 standard deviations. So that means that we are looking at 2 standard deviations to the left, which would be right there, and that's 115. And that's in between, from there to 2 standard deviations to the right of the mean, which would be 155. Okay? So our answer to our question, we would expect 95% of the women's weights to be between 115 and 155 pounds. Now, that's nothing new from what we did in the first semester when you're talking about the normal distribution. Where it gets new is in part B. If a randomly sampled 10 women at the university, how close do you think their average weight would be to 135 pounds? Okay. Now, we're no longer looking at an individual woman. We're looking at a sample of 10 women. So we might have an individual woman who is right there around the mean. We might have one that's lower than the mean, a little bit above, but they average out to something right around the mean for the entire population. So you're looking at the average of the sample. So we would expect most of their weights to be right around the middle, 135. Now, if we were to take a sample of 1,000 women like we have in the second part, we know from the law of large numbers that that mean should get closer and closer to what we expect in the population. So if our previous answer, when our sample size was only 10, was somewhat close to 135, we would expect this to be much, much closer to 135. Okay? In fact, pretty much exact. So, for what to expect with these sample means, okay, we want to estimate the average weight loss. Here's our example problem for the lesson. We want to estimate the average weight loss for all of the people who attend a national weight loss clinic for 10 weeks. Now, kind of like what we saw when we were talking proportions, we don't typically know what that population value is. So in this case, it's unknown to us, but the average weight loss, the mean weight loss for the entire population is 8 pounds, and the standard deviation is 5 pounds. Okay, so those values are expressed, population mean is expressed with the Greek letter mu. We've used that before. So that's 8 pounds, and the population standard deviation is represented with the lowercase sigma. That's 5 pounds. Now, these weight losses are approximately bell-shaped. 95% of the individual weight losses will fall within negative 2 pounds, which would actually be a gain of 2 pounds. And a loss of 18 pounds. Okay, so again, you could visualize this with the normal curve. Okay. Our mean goes right there at the center with 8, and we have a step size standard deviation of 5. So 2 steps to the left would take us down to -2. So again, a weight loss of -2 pounds would be a weight gain of 2 pounds. And then 2 standard deviations to the right. So +5, +5. We're at 18 pounds of weight lost. 95% of the individuals would be between those two values. Now, from this population, we are going to take a bunch of samples of size 25. Now, there's some variation within each of the samples. Our first sample, we can see that the average weight loss was 8.32 pounds, and the standard deviation was 4.74 pounds. Okay. Sample 2, you can read that, 6.76 pounds was the mean there. Standard deviation was 4.73. And sample 3, sample 4. We know that there's some variability within each of our samples. Now, that doesn't have to match the population exactly, but you can see they're all pretty close. Remember that population mean mu was 8 pounds. Okay, our sample means, we're going to represent those with the symbol x bar. Okay. So in this case, we have x bar 1, x bar 2, etc. Some of those are above 8, some of them are below 8, but you can kind of see where we're going. The big idea is that all of these sample means should average out to become that population mean of mu. Same thing with the standard deviation. We know that our population standard deviation was 5. Okay. All of our standard deviations here, a couple below 4 or below 5, a couple above 5. But the big idea that we're working towards is that they will eventually average out to be about the same as that population mean of 5. Okay? These individual sample standard deviations are just used with S. Okay, so sample standard deviation 1, sample standard deviation 2, etc. Now, we do have some rules that need to be satisfied in order to use the equations that we're going to look at in just a second. Okay, these conditions, again, they are given in the document at the top of this page. And we want to confirm before using these rules using these equations that these conditions are met. So we need to have a population of measurements that is bell-shaped, meaning it's normal, and a random sample of any size is measured. Okay? That's what we have with this weight loss example that we're going through. However, if the population is not a normally distributed set, and that's okay. As long as we have a large enough random sample that is measured and a sample size that is 30 or larger is considered large enough. However, we know that if there's a lot of variation, especially if we have extreme outliers, the bigger the better. But 30 is considered the minimum in order to use these conditions for these sample means. So, similar to what we saw with proportions, we are fitting all of these samples of size n onto its own normal distribution. That's what this rule says. If we take numerous samples or repetitions of the same size, the frequency curve of the means from various samples will be approximately bell-shaped. And the mean, okay, we average all of those sample means together and it will become the population mean, mu, right there at the center of the curve. The standard deviation for this that is found with this equation right here. So we take the population standard deviation, which was sigma, and divide that by the square root of the sample size n. So this is the standard deviation for this distribution right here. Remember that the standard deviation is this step size. Okay, so that's what allows us to get from there, from the mean out to each step incrementally. So let's take a look at an example problem here. And in that weight loss example, the population mean and standard deviation we know were 8 pounds and 5 pounds respectively. And we're going to say that we're taking random samples of size 25. That means that the potential sample means must be represented by a bell-shaped curve with the mean of 8 pounds. So that mean of 8 is going to go right there at the center of the curve. And the standard deviation, again, our equation for that is population standard deviation divided by the square root of the sample size n. So our population standard deviation was 5, sample size was 25, square root of 25 is 5, 5 over 5 gives us 1 pound. Nice and easy to work with. So that's our step size going to the right, 9, 10, 11. Going to the left, 7, 6, 5. And once again, we could apply our empirical rule, and you can see that below. There's a 68% chance that we take a sample of 25 people and that their average weight loss for that sample is going to be between 7 and 9 pounds. Okay? Extend that out another standard deviation in both directions. A 95% chance that the average weight loss for that sample is between 6 and 10 pounds. And we are 99.7% sure, okay, almost certain, that that sample mean is going to be between 5 and 11 pounds. Now again, think about what this bell curve represents. Okay, taking a bunch of samples of size 25 and the average of those samples. Okay, so going back, okay, these are examples of those samples that were taken of size 25. This is not the same curve as what we have right here. This is for the individual. That's what we did in the first semester. An individual person selected from the population. Now we're looking at a sample of size 25 and the average of those averages. Okay, that's what's going on here. That's a big concept to understand for these sections. Now, those samples of size 25, that gave us a standard deviation for the distribution of 1 pound. Okay. Let's expand that sample size, and let's suppose that now we're taking samples of size 100. So here's our equation for standard deviation. The only thing that's changing is, because the population standard deviation stays the same, the only thing that's changing is our sample size. So now square root of 100 is 10, and 5 over 10 is half of a pound. So now our distribution is going to look a little bit different, in that we still have the same mean, average weight loss of 8 pounds right there at the center, but everything is a little bit more compact, and it's 7 pounds right there, 10 pounds out there to the right, 2 standard deviations to the right. I'm sorry, that would be 9 pounds. And it took us 2 standard deviations. So now there's a 95% chance that that sample mean is going to be between 7 and 9 pounds, when previously there was only a 68% chance that it was between 7 and 9 pounds. Okay? The bigger the sample size, the more certain we are with our estimates. Larger samples tend to result in more accurate estimates of the population values than do smaller samples. Okay? If you observe these trends happening over a larger sample, you're more certain that that's what's actually happening in the population. So we've been looking at both proportions and means. Proportions of the population, sometimes you're describing categorical data with that. The means, you're usually talking about measurement variables. Okay? There are lots of other situations and similar rules apply if you get into an advanced statistics course later in your career. So here's a quick case study to just kind of summarize everything. Looking at the 1994 midterm election, there was a telephone poll done of 800 adults 2 days after the election, and 56% of the people surveyed reported they had voted in the election 2 days prior. So that's a pretty quick snapshot there. After more time had passed, the Committee for the Study of the American Electorate, they did a more thorough study of the voting results and found that really only 39% of American adults had voted. There's quite a discrepancy here between the 56 that said that they had voted and determining that really only 39% of all registered adults had voted. Now, could that discrepancy just be the results of random chance, natural variation? Okay, you expect this, you got this, no big deal. Or are those numbers so far apart that it seems pretty suspicious that there would be that discrepancy? Well, what we can do is go back and use our equations for proportions. So let's accept that that 39% of American adults voting is the true population value. We can do a standard deviation calculation here, where that 39%, the sample proportion, p hat, that will go at the center of the curve, 0.39, and the standard deviation is calculated by multiplying by the complement, 1 minus 0.39, divided by the sample size, 800, take the square root. We get this as our standard deviation, okay, 0.017. Now, to step that out and apply our rules, that we can see that's a pretty small step size, about 2 percentage points. So this would be 0.41 approximately, 0.43, 0.45 would be 3 standard deviations to the right of the mean of that curve. Okay, so 45%. In the survey 2 days after the election, it was reported that 56% say they had voted. Okay? For us to get something that far away from what we would expect, if we were to do a z-score calculation, here's what we observed, here's what we expected, that difference divided by this standard deviation, this value is 10 standard deviations to the right of what we would expect. That is incredibly unlikely. So that makes us suspicious, and something went wrong here. So we'll get that into how we interpret these conclusions in the coming days.